investigation of econometrics, and today we will start our discussion about the sampling distribution of OLS estimators. So let me briefly remind you what do we know at the moment. We introduced the linear regression model where the variable of interest y is represented as the sum of two parts. So one part is the conditional expectation of y given x, which means that if I have some information about x, I have a chance to predict the value of y. And I believe that this relationship is linear. So that's why we call this linear regression model. But of course, in reality, y is not deterministically connected to x. Therefore, we have the error term, which is the effect of other factors not included in the model. We had this discussion in the second lecture. We spoke about different examples of this. And given some practical application, we don't know these two parameters, beta 0 and beta 1. So we need to estimate them with the help of data. And doing this, we are basically doing the same steps as in statistics. So all the ideas about estimation are applied here. But the method for estimation for deriving the estimators is called ordinary least squares, and we derived that with the help of data, we can estimate beta 1 with the following estimator. So based on the data, we can get the following number, and beta 0 can be estimated in the following way. So once again, please be careful. You're already familiar to all these concepts, that this is our theoretical model. This is our belief that we think that x and y have this relationship. This is calculated based on the real data, based on numbers, and given that the sample is random, we first of all, with the help of these estimates, we are able to build the estimated regression model. So please keep in mind that these two things are different. This is the population model. This is our belief. This is the theoretical concept, if you want. And this is the result of our actions. This is the result of our calculations. And the outcomes of beta 0 and beta 1 here, and also u hat, depend on the sample. And if you derive another sample, you will probably get the different values of beta 0 and beta 1. Therefore, these estimators are random numbers, random variables. What also we know, we are able to evaluate how good this model is able to explain the variation in y. So basically, we calculate for this the measure called r squared. This is the fraction of the sample variance of y, which is explained by x, which is explained with the help of our regression model, estimated regression model. We divide sum of squares, regression sum of squares, by the total sum of squares. And finally, we concluded the last lecture with the estimator of the standard deviation of the regression error. Why do we want to know the standard deviation of this error? Because it gives us some understanding of the precision. If u deviates not much, then the model is good in explaining why. And since we don't know this error term, we estimate it with the help of residuals u hat, and then we compute the sample variance of these u hats. This is here. While computing sample variance, we divide u hat squared by 2, because now the degrees of freedom must be decreased by 2, because u hat is computed with the help of two estimates, beta 0 and beta 1. If we are calculating the usual sample variance, we decrease the number, the n by 1. Why? Because the usual sample variance depends only on x bar, only on one estimate. But here you had depends on two estimates, beta 0 and beta 1. Therefore, we decrease the number of degrees of freedom by 2 here. And also this sum is called the residual sum of squares. So this is what we know at the moment. And today we will extend the idea of randomness of these estimators. So this lecture is going to be more, let's say, conceptual than practical, but still all the things that we are going to discuss are quite important, and you need to keep them in mind throughout the whole course. And if you would like to apply these methods in the future, you also need to be careful with all these things. So let's try to go deeper into the idea of causal effects. We started this discussion in the first lecture, and we established some, let's say, idea that causal effects of one variable or some treatment on the outcome can be established with the help of randomized control experiment. So we had some homework on this. Well, in the last lecture, we also claimed that the linear regression model can be used to make predictions. When we estimate beta 0, when we estimate beta 1, and when we know some number of x, we can make a prediction. And sometimes this linear regression model is used for these predictions. But also beta 1 has another interpretation. So the number that we estimate has an interpretation of the causal effect on y of a unit change in x. These are two different things, and we tried to establish this distinction in the second lecture. When we introduced the linear model, I said that first purpose of this linear model is making predictions, and the second purpose is to estimate quantitative effects of change in x on y. And that's exactly what we are going to talk about. So what is beta 1 in mathematical terms? If you take a derivative of this conditional expectation with respect to x, we have beta 1. So mathematically, what is the derivative? Derivative is the change in dependent variable given a unit change in the independent variable, right? So if x changes by 1 unit, the conditional expectation of y changes by beta 1. So it's here. If delta x is 1, delta y on average, so basically delta of the expectation must be beta 1. Well, because x can take multiple values, x is a continuous variable, the causal effect of a given change in x is beta 1 times delta x. So x is not changing by 1 unit. X can change by 2, 3, 4, 5 units, and so on. This is going to be delta small x. And then we take beta 1 multiplied by this change in x. And we can predict the causal effect of this change on y. If somebody remember, how can we establish the causal relationship among variables? So what must be done practically if you want to ensure this causality?
Do you mean what we want to do to find this relationship?
No. How exactly must be the data obtained in order to ensure
Randomly.
that
Randomly.
so first of all randomly, but then if we want this causality, if we want to say, well, something causes something,
Yes,
like,
we
I
need
don't
to
know,
give one group, divide them into two groups, and then give one group with a placebo, and the second is the real medicine, something like that.
yes, that's a perfect answer. So, and we need to do this randomly. But now, look, if we have only two possibilities, treatment and control group, then we can estimate the causal effect with the familiar difference in means, right? So what you did yesterday on your midterm. So you need to compare two sample outcomes. One sample is a treatment group, one sample is a control group, and your x takes values 1 and 0. In our case, x is not binary. In our case, x is continuous. So, but the idea is still the same. So we want to conduct a randomized control experiment, and x must be randomly assigned on the objects. We will discuss several assumptions, additional assumptions, when OLS is able to estimate this causal effect, and we need to be very careful with them, because otherwise we are not able to claim that X causes Y. It's simply just some association, but not the causal effect. So just to illustrate this idea, let's go to the example that we used, this California school districts example, and on the last lecture we estimated beta 0 and beta 1, and we've got this OLS regression line. So now let's give the practical meaning of to this estimate minus 228. What does this mean? If you take the derivative of test score hat with respect to student to teacher ratio, we get this minus 228. And this means that if we increase, for example, if we increase student to teacher ratio by 1, so if the number of students per one teacher increases by 1, on average, it will be followed by the decrease in test score by 228 points. So this is the quantitative measure of the causal effect. So the causal effect of an increase in STR by 1 unit is minus 228 points to the student to teacher ratio. If STR increases by 2, then we multiply 228 by 2 and we have 456, right? So the test score will decrease by 456 and so on. So that's an idea, and that's the meaning of this number. But once again, we must verify that necessary assumptions hold. So the assumptions that allow us to claim that this minus 228 is exactly the effect of student to teacher ratio. Well, basically this question is one of the most important questions in the whole econometrics course. It's not about mathematics, it's not about some derivations and statistics, it's mostly about the verification that assumptions needed to give this number a sense of a causal effect, these assumptions hold. So what are these assumptions? So if you have a linear regression model, we can give beta 1 the causal effect interpretation if, first of all, the error term has conditional mean 0 given x. So mathematically it's this. Practically, we will discuss it a bit later, and this is the most important assumption in this sense. Two other assumptions are more technical. So, second assumption is familiar to us. We want to obtain the sample for the estimation through the random sampling, and therefore these pairs of x and y's must be independent and identically distributed rows from their joint distribution. So this is familiar. This is the same condition as we had in statistics when we started our discussion about the estimation. And number three is also, it has some practical application we will see. The large outliers are unlikely. So this is the assumption in words, and more technical definition of this assumption is the following. So x and y have non-zero finite force moments. So first of all, why these assumptions are important and why we should care about them and why we are spending our time on this. So first of all, with the help of these assumptions, they help us to ensure that in large samples, OLS estimators are consistent. So it means that they point to the unknown population parameters, and their sampling distribution is normal. So, and this help us to do what? If we know that sampling distributions are normal, so what it gives us? What it gave us in statistics. We believe that sampling distribution of x bar, for example, is normal in large sample.
That we can use like t-statistic.
Of course, we can make t-statistics, we can use t-statistics, and then we can build confidence intervals, we can make hypothesis tests, and we can make all these funny things that we were doing in statistics. So that's why we should care about these assumptions. So because it gives us an opportunity to apply all the familiar things about hypothesis tests and about confidence intervals. And the second thing is that with the help of these assumptions, we can organize the circumstances when it's difficult for OLS estimates to show us the causal effects of B1. So that's what we start doing probably in 2 weeks or in 2 lectures afterwards. So we will try to come up with some situations when this linear model doesn't work. Okay, so let's try to understand what the first assumption means. I want to warn you here that this first assumption, it's one of the most crucial assumptions, and whenever you read any paper that uses OLS estimators, you will see very long and very detailed story why the author believes that this condition holds. What does this condition mean and why this is important? So for the estimation of causal effects, as we know, x must be randomly assigned. So the simplest case, if x is 1 or 0, 1 is treated, 0 is not treated, then, as Vladimir said, we must randomly assign treatment and control, we must randomly assign treatment and placebo on the participants of our experiment. as we also know, in many cases, this is not possible because we are working with the observational data. We cannot conduct experiments on people, especially in economics. That is why it must be as if randomly assigned. So we believe that this is randomly assigned, but not exactly. So for example, what might be as if randomly assigned? The birth date of a person, right? So we are not making experiments on people when they are born, but basically the birth date is more or less as if randomly assigned to the person. We can also think about, some natural disasters as if randomly assigned, like some floods or tornadoes or earthquakes. We are not making these experiments, but definitely these natural disasters, they happen as if random. So therefore, we usually try to look for some x that is not randomly assigned, but probably as if randomly assigned. So we'll talk about this a bit more in the future. So what is U? Basically, what we are talking about. U is the effect on Y of all other factors that are not included in the model. And what does this condition mean? So this conditional mean of U given X is 0. It means that all other factors contained in U must be unrelated to X. So there is no relationship between X and all other factors that are not included in the model. This is why we are making this random assignment of treatment. So given a value of X, the mean of the distribution of these other factors is 0. We are not able to predict how these other factors will affect the outcome variable. In the randomized control experiment, as I said, subjects are randomly assigned to the treatment group when X equals 0 or the control group when X equals 1. And what it gives us? It gives us that X is distributed independently of the subject's personal characteristics, including those that determine Y. So for example, when we are trying to test some drug, some vaccine, and we ask a person, would you like to get a placebo or would you like to get a real drug? So probably the personal characteristics of the participant will somehow deviate the decision, right? So people who are healthier, who probably believe more in medicine and pharmacy, they will ask to give them the real drug. So people who are participating in this experiment because of money and they are not sure about their health, they probably would prefer to get a placebo. And in this case, there are personal characteristics that can influence the outcome, and the outcome here is going to be the speed so the period of time when the person becomes healthy, it's going to be influenced by the personal characteristics, and we don't want this to happen. That is why we not ask people about their choice. We assign them randomly. You get the treatment and you get a placebo. And in this case, we ensure that this condition holds, because this is just a mathematical formulation, but the practical formulation means that we must be sure that nothing influences the treatment. Yes, because of the random assignment, the expectation of U given X is 0. In observational data, X is not randomly assigned in an experiment. So this is the problem for us. And the best we can hope that X is as if randomly assigned. Probably not. We don't know. And how should we deal with this assumption? So usually it requires the careful thought and judgment. It is not verified mathematically, or almost not possible to verify this mathematically. We will talk about some potential signals that this assumption doesn't hold, but usually it is not from mathematics. It's from your knowledge of the field. You need to understand the processes and mechanisms that you are investigating. And in this case, sometimes it looks difficult because you cannot simply learn this and then reproduce on the exam or anywhere else. It needs from you some kind of, how to say, some kind of erudition, right? So you need to know how things in the world are organized. So let me show you an example. What does this mean? Well, yes, basically for making predictions, this assumption is not crucial. That is why the data science is somehow different from the economic science. So in the data science, we want to make predictions. We don't care about all the things, and we simply want our model to give us the best possible prediction. But on the other hand, if you want to tell the meaningful story, if you want to say, well, this influences this, you must be careful with this assumption. So what does this mean? Let's see on the example, because I'm talking a lot about this, but probably it's not that clear what are we talking about. So back to the class size example. The class size is just one of many factors that influence the test score. So can you give me some other examples? What else can influence the test score?
Father job, mother job.
Okay, yes, we know this. For example, father, mother job. Something else.
No, there are many factors, for example,
Just
even the
give
temperature in the
Teachers.
classroom. Temperature in the
Well,
classroom can
even the
influence.
temperature in the classroom, yes.
It just features of this class. For example, equal people in this class study.
What do you mean equal people? Equal in what sense?
Okay, just forget.
No,
I don't know
it's
how
okay. I mean, just
like
give some particular numeric measure. So look,
okay,
we
in the
can
first
measure the
lecture,
temperature in the class. We can somehow measure the mother and father job with the help of factor, right? So 1, 2, 3, 4, and which is gonna be like in ANOVA. In
for
what
example,
sense?
I remember from the second lecture about graphic, you said that, for example, rich family have higher like
Yes, so something like the family
opportunities. So
income. Family income, because
yes,
probably depending on the family income, students might have some additional classes and they may perform better on the test. Yes, so that's true. And look, so now we need to think. So first of all, let's list some of the factors. So one district might have better teachers because also the nature of teacher might influence the outcome of the test score. It might use better textbooks that are more appropriate for this test. Even if you have two districts with comparable class sizes, with similar teachers, with similar textbooks, they might have different student populations. Exactly what Arina said about about the equality of people. So for example, one district might have more immigrants or welfare people, and it still produces some deviation of the test score. So even if two districts are the same in all ways, they might have different test scores for some random reasons, like the temperature in the classroom, for example. So we are not able to list all the possible factors, but here we must ask the question. So the error term in the class size regression represents the contribution to test scores made by all these omitted factors, right? So this error is exactly how two classes with the same student to teacher ratio may differ because of average family income, quality of teachers, average percentage of immigrants, something like this. Now, what is the most important question here? Do we believe that all these omitted factors are not related to the class size? Or say it differently, is this possible that larger class sizes tend to have, let's say, less or poorer families? Is this possible that this...
Yes, there is a...
It's possible, right? Because probably if the classes are large, then the municipality that gives money to these classes is not rich. And the municipality is not rich means that families living in this district may also not be rich. And in richer places, the class sizes might be smaller. Or if we have districts with a higher percentage of immigrants, they also might have larger class sizes just because there are more people living in this district. Therefore, look, we are not doing mathematics here. We start thinking about, and we logically come to the conclusion that the omitted factors like families' income or the percentage of immigrants, and even probably the quality of teachers. Because if the district is richer, first of all, it is able to make classes smaller, to hire more teachers, and probably to hire more qualitative teachers, right? Because the district is able to pay more money to these people, and they will come to these schools. So therefore, we are not sure that all these omitted factors are unrelated to the class size. And going back, we are not sure that this assumption holds. That's a problem. That's how you need to verify this assumption. You need to start thinking about, well, do I miss some other possible factors that influence the test score and that might be connected to the class size? If you miss such factors, and if there is some degree of certainty that these factors might be connected or might be somehow related to the class size, then we are in trouble, because this assumption does not hold. Well, this is, let's keep this question until lecture number 6. In the lecture number 6, we will come back to this question and we will start our discussion with the ways how to solve this problem. But first of all, I want you to understand what is the problem and how this problem can be formulated. And this is exactly the assumption number 1. So the assumption is always, this assumption always holds if you run the randomized experiment. Once you don't do this because of the observational data, you need to start thinking about the omitted factors and if these factors are connected to the, for example, class size, to X. And if they are, this assumption doesn't hold. And this is the problem. So how to solve this problem, we will discuss in the lecture number 6.
For now, we just assume it.
For now, we assume that it's okay. I mean, we keep working that this assumption holds, but we already see that for the class size example, this assumption doesn't hold. Because practically we somehow discuss that this is possible, that wealthier districts might have wealthier families living there, smaller class sizes, but still these are our just assumptions. We first of all, we need to verify this somehow, and if we are able to verify these assumptions, and if we are able to conclude that the assumption number 1 fails, then we need to solve it somehow. So the best solution is to run a randomized experiment. Given the problem, given this example, it's not possible because you cannot randomly assign the class sizes over districts. Definitely, it's not practically feasible. Then we need to solve this problem somehow else. And how to solve it, we'll discuss in lecture 6.
And also you said that it is not crucial in data science, but crucial in economics, right?
Look, once again, it is not crucial if you don't want to claim the following thing. When I decrease student to teacher ratio by 1, the average test score increases on average by 228. If you don't want to claim this, or in this way, the assumption number 1 is not crucial. If you want to claim that, well, if I, for example, you are in charge of making the decisions in the education system, and you want to improve test scores in your district, and the data scientist brings you this regression and says, well, if we decrease student to teacher ratio by 1, we can expect the increase in test scores by 228 on average. If you fail to prove that assumption 1 holds, then this 228 is not valid. But still you can use this for making predictions, like if student to teacher ratio is 20, the average test score is going to be equal to something.
Okay.
So the causal effect means that it's like, if I change this, then the result is going to be this. So this is the causal effect. If I do something, then there is some result. And in this case, when assumption 1 doesn't hold, you simply fail to give the quantitative measurement of this causal effect, because this 228 is not going to be true, and we will see this. Okay, so assumption number 2. It's something simple. We know this, just let's repeat. What does this mean that X and Y are independently and analytically distributed across observations? So first of all, we believe that observations are drawn from simple random sampling, by simple random sampling from a single large population. Even for the observational data, it's possible. When you collect the observational data, you randomly select districts for example, or people, or respondents, firms, households, the objects that you study, and that's how you establish this IID assumption. So all the data sets that you had yesterday on the midterm were collected through the simple random sampling. So you make some survey, you ask random people on the different questions and get the data. So you don't need to run the randomized control experiment for this. You simply, even for the observational data, you simply collect this data through the random sampling. Well, what does this mean, identically distributed? It means that if you, for example, collect a sample of n districts from the population, then these pairs are going to be distributed identically. So it means that their distribution is the same. And if you do this randomly, if one particular observation doesn't depend on the other particular observation, then they are distributed independently. Which means that your population must be large, such that if you pick one observation, it doesn't influence the probability to pick another observation. But on the other hand, your sample also must be large, but still relatively small to the population. Well, not all sampling schemes produce IID. We also discussed this in statistics. For example, if you set values of X yourself as a researcher, those are not randomly selected, and that's why those are not independently distributed. Or when, for example, we work with the observations of one unit over time, which is called time series data. So time series data is going to be studied in the second part of econometrics next semester. So we also will discuss how to deal with those issues when observations are not independently distributed. And assumption number 3, it also has some practical application before estimating OLS and before applying OLS and before estimating beta 1 and beta 0, you must verify that there are no large outliers in the data. So what does this mean, outlier? It means that you have some observations with values X and Y, or both, that lays far outside of the usual range of data. So it's some untypical observation, non-typical observation. It's either large or small. So why this is crucial? Because if you remember how we calculate, for example, sample mean. Sample mean is calculated when you add all the observations and then divide by their number. And suppose that one observation is very large. Then the whole sample mean is going to be deviated, right? So it's going to be deviated in the direction of this outlier. So the means are sensitive to outliers. The same story is with OLS estimates, because OLS estimates are also sensitive to outliers. So that's why we want to get rid of them. So large outliers make OLS regression results misleading. And well, mathematically, if you want to formulate this assumption, it means that X and Y have non-zero finite fourth moments. You also can see something like this. So the fourth moment of X must be positive and less than infinity, and the fourth moment of Y the same. It must be positive and less than infinity. Or we also can call this that X and Y have finite kurtosis, for those who remember moments from statistics and their names. So how to find outliers? One way, and sometimes this is the most, let's say, practical way, and the simplest way is to plot the data. So let me show you how to do this, and then we will go back to the slide. So look, here is the data. We have all the observations that are close to the horizontal line, and one observation here. So this is how you can identify outliers. You have a group of observations which is concentrated in one place, and then one observation which is far away from this group. And look what happens. If you drop this outlier, all the other observations belong to this horizontal line, which basically, if the line is horizontal, which means that if I change x, nothing happens to y. There is no relationship between x and y. But if I include this outlier, look, the OLS regression line pivots, and it has now the positive slope. And the positive slope suggests that if I increase x, y will be also increasing. That's why outliers are not welcome in the data, because with these outliers, you can get the misleading results from the OLS estimation. And what to do with them? Well, the problem is how these outliers appears in the data. If, for example, there is a data entry error, well, the person who collected the data just made an error and put there like extra zero or something, like here, right? So it was around 200, and the person put there 2000, or like 180, and instead of 180, there is 1800, right? So 10 times greater. If you suspect that this is the data entry problem, then just try to correct this error. If it's not possible, just drop this observation from the data set, because it has no additional value in the data set. It will just totally deviate the correct estimation.
Is it the same thing like we did in with box plot that was with the medians?
Yes.
Well,
Something
yeah,
like this.
percentiles.
When you build a box plot, in the box plot you also see some circles, which are data points that are potentially outliers. The only thing is that, well, you must be careful how the box plot identifies these outliers. There are many formal algorithms how to catch outliers and identify them. I'm not going to discuss them in this lecture, so we will stick to the easiest kind of visual way of identifying them. If you have some data point that is far away from the usual location of these points, then you believe that this is an outlier, and probably you drop this, or you can correct if there is an error. Yes, with the box plots is also possible. You have these whiskers on the plot, right? And if something appears above or below this whisker, it also might be considered as outlier. There are fancier methods of outliers identification in machine learning as well, but so I'm not going to discuss them. Okay, now, so these are three assumptions. We must be very careful with them when we practically apply OLS. Basically, I can tell you that when I'm reading some like papers published by like master students or bachelor students, they usually fail to think about these assumptions. I am not sure why do they do this. Probably they just don't care. But then if they don't care with these assumptions, the results that they pretend to be valid and somehow you must believe to these results the results are just they are nonsense. So you don't believe the results because the assumptions are not proven to be hold. So that's why, please, if you are going to apply these methods in the future, make sure that all three assumptions are somehow verified, and especially the first one with the zero conditional mean. As I said, almost, well, I cannot say how much, but the large part of econometrics is devoted to the mediations of the cases when this assumption doesn't hold. Keep in mind always that anything that you estimate with the help of data is random. So therefore, these OLS estimators, beta 0 hat, beta 1 hat, are randomly drawn. So they are computed from a randomly drawn sample. Therefore, they are random variables. Any random variable has a probability distribution, and in the case of statistics, and beta 0 and beta 1 has are statistics as well, these probability distributions are called sampling distributions. All these concepts are familiar to you from statistics. In large samples, so I'm leaving this without any kind of proof. So if you are gonna study econometrics in in your master level probably, or like PhD level, you will definitely have the proofs of this, but we will just believe that in large samples, the sampling distributions of beta 0 and beta 1 hat are approximately normal. With the help of, we can prove this with the help of central limit theorem. And if we believe that the sampling distributions in large samples are normal, what do we want to know for the normal distribution is expected value and variance. Because if we know expected value and if we know variance of a sampling distribution, we are able to conduct hypothesis testing. We are able to build the confidence intervals, and we are able to do a lot of other funny things. So we will start with the mathematical derivation of the expected value of beta 1. Basically, this is going to be the only derivation in this topic, because all the other derivations I will just omit and I will give you some results. The calculations related to these derivations we will do in the next exercise session, so you will see how to calculate all the things manually. But why I leave this derivation? Because it's going to be crucial for the subsequent topics related to the conditional zero mean assumption and when it fails. So let's take one particular way of beta 1 hat calculation. So we know that the OLS estimator for beta 1 might be calculated like this. So now, if we believe that Y, the population regression model, looks like this, and then we can take the averages from the left and the right hand side of this population regression model like this. So this is the population model. This is also population model. So look, no estimators here. All the parameters are population parameters, constant unknown parameters. So now, now we take the difference. We subtract the second from the first. So we have this. And we can see that in the formula for beta 1 hat calculation, we have this difference, and also we somehow express this difference in terms of beta, x, and u, error term. So logical to take this part and plug it here. So let's do this. So we plug into beta 1 hat and then make some algebra. So first of all, instead of this difference, I plug this expression, it's here. And then I hope the further steps are obvious. So we open these brackets, we multiply xi minus x bar by this xi minus x bar with beta 1, and then xi minus x bar by this. So it's here. What do we have? Okay, so before asking this, let's make one more step. Beta 1. Beta 1 is constant. So we can factor beta 1 out of this summation sign. And then we can divide term-wise the whole fraction by the sum of this xi minus x bar. It's here. So now, in the first term, we see that this sum and this sum just cancel each other. And we have beta 1. And in the second term, we have something like this. Okay, so that's basically the end of the expression where we want to write beta 1 hat as the function of beta 1 and something. And this will be important for us in all the other topics. So this is this expression. So we must somehow remember this expression for the future. So by the way, if I divide the denominator by n, what is this?
Variance.
It's variance, yes. Oh, by n minus 1, it's going to be the sample variance. What is this? If I divide it by n
Standard
minus 1.
deviations.
No, it's not standard deviations. I take
Just
one
deviations.
deviation, multiply by the other deviation. What is this?
Square sum of
No, it's
squares.
sample
What
covariance.
was it?
It is sample
Covariance, right.
covariance. It is sample covariance of x and u. By the way, do you remember? If two variables are not related to each other, if they are independent of each other, how much is covariance?
0.
It's 0. Therefore, I hope you see why assumption 1 is crucial. Because if x and u are not related, then this thing must be 0. This covariance must be 0. And if this is 0, beta 1 hat is going to be equal to beta 1. But that's not what we want, because due to the random sample, in the numerator we might have some other number close to 0 but not exactly 0. What do we really want is the following. But that's nice if you see that in the numerator of the second term, we have something that measures the mutual relationship between x and u, if they're related or not. What do we really want at this moment is the following. What is the expectation of beta 1 hat, knowing this decomposition of beta 1 hat? So we will start with the conditional expectation of beta 1 hat. So beta 1 conditional on x1, x2, and xn. So what does this mean? It means that if I know x1, x2, xn, if I already collected these numbers, what is my expectation of beta 1 hat? So this is going to be the conditional expectation of this expression. And we know that expectation of a sum is a sum of expectations. So therefore, I can write it like the expectation of beta 1, given x1, x2, and so on, plus the expectation of this term. So beta 1 is constant. What is the expectation of constant?
The same.
It's just a constant, yes. So it's just beta 1. in this case, look, x1, x2, and so on are known. So I know these numbers. Therefore, these expressions are also known. And the only unknown thing for me is u, the error term. So this is the random part of the whole term here. So I can basically, there are several steps here, but I decided to make them shorter. I can move this expectation here. And I have expected value of ui minus u bar given x1 to xn, given the values of x. So how much of the error term I expect given the observed values of x1, x2, and so on. So now the question is, how much is this? If assumption 1 holds, how much is this expectation?
0.
It's 0, because if assumption 1 holds, then expected value of u given x's is 0. And also after some derivation, u bar is also going to be, expectation of u bar is also going to be 0. Yes. So first of all, ui does not depend on x's except for xi. So therefore, this conditional expectation equals to simply the conditional expectation of ui given xi, no x1, x2, and so on. And then, given the assumption number 1, this conditional expectation is 0. So that's why conditional expectation is crucial. Because if assumption 1 holds, we can prove that expectation of beta 1 hat is beta 1. And we can prove that, well, first of all, yes, by the first least squares assumption, this conditional expectation is 0. And if this holds, then we can prove that expectation of beta 1 hat is beta 1. What does this mean? It is unbiasedness. We spoke about unbiasedness in statistics. We have seen that there are biased estimators and unbiased estimators. In this case, this is why, for example, when we calculate variance, sample variance, we divide by n minus 1, because when we divide by n minus 1, the estimator is going to be unbiased. Otherwise, it's going to be biased. The same story here. If assumption 1 holds, then we can prove that beta 1 hat is unbiased estimator of beta 1. What does this mean, unbiased estimator? It means that this random variable as an expectation has beta 1. And this is the crucial feature, crucial characteristic of estimator. We want the estimator to be unbiased. And look, if this condition doesn't hold, then this is not 0, and we have some mess. We have some additional term to beta 1 that is gonna deviate our estimation either to the left or to the right. And this will give us a lot of problems. That's exactly why I said that the numerical meaning of causal effect of beta 1 is not gonna be true if the first assumption doesn't hold. So we will talk more about this bias and how to deal with this bias later. So at least for now, if we believe that assumption 1 holds, then OLS estimator for beta 1 is unbiased. The expected value of this random variable is beta 1. So we are shooting exactly in the direction of unknown goal. So now for beta 1, for beta 0 hat, this is very simple. So we know that beta 0 hat is y bar minus beta 1 x bar, beta 1 hat x bar. So we know the expectation for beta 1 hat already. So now if instead of y hat, y bar, sorry, I will write down this expression, beta 0 plus beta 1 x bar plus u bar. You see that it splits into 4 terms: expectation of beta 0, expectation of this, expectation of u bar, and minus expectation of this. So this is a constant, this is beta 0. So here I can take beta 1 out of the expectation sign. That's going to be the expectation of x bar, which is just x bar, if it's going to be the conditional expectation. Expectation of u bar is 0, again, if I believe that assumption 1 holds. And here it's going to be the expectation of beta 1 hat multiplied by x bar. And what is expectation of beta 1 hat? I know that this is beta 1, so I plug it there, and finally I have beta 0. So this is why assumption 1 is crucial, because it gives us a way to prove that both beta 1 hat and beta 0 hat are unbiased.
Where did the error term go?
The same story. So basically I made it a bit shorter. We also need to start with the conditional expectation first and then make it unconditional expectations. The error term, the expectation of u bar is what? So what is u bar? It's u1 plus u2 plus u3 divided by n, right? So this is the mean, sample mean of u bar. And then I know that the expectation of u1 is 0, expectation of u2 is 0, expectation of u3 is 0, and so on. So basically the whole sum is 0. So that's why this expectation becomes 0.
Okay. And can't we get rid of it like in the first line of derivation, in the expected value of, yes, this whole thing, we have a beta 1 multiplied by mean x minus, and there is a beta 1 hat multiplied by mean x.
But look, these two things are different.
Yes, I
beta 1
see,
is a
but
constant, beta 1 hat is a random variable.
didn't we like prove that estimate of beta 1 is beta 1? No?
Yes, that's here. That's what we use here. Expectation of beta 1 hat is beta 1, and then we have this term, and this is also going to be beta 1 x bar, and that's how we cancel them.
Oh, okay.
So we know expectations. We know that expected value of beta 1 hat is beta 1, expected value of beta 0 hat is beta 0. That's the same story as we had, for example, in statistics, when we spoke that expected value of sample mean is the population mean, expected value of the sample variance, for example, is the population variance. The same story here. We showed that expected values of our sample estimates equal to the population counterparts. Now, the second characteristic that must be known is variance. So with the variance, I will not present you how to derive the variances. Once again, why I decided to present you these expectations just for this? Because we really need to know this expression, and this expression is going to be used later on. So that's why it would be nice if you somehow know where to look for this expression. But for variances, it's a bit complicated, so that's why I just show you the formulas, how the variance of beta 1 hat looks like and how the variance of beta 0 hat looks like. Yes, so here we have the term hi, which looks like this. Why do we need to know about these two variances? Yes, why do we need all this? First of all, it has also some practical meaning. What you must do if you want to produce the quality model, if you want to produce the model that is good enough, let's say. Look, variance of the estimator, it shows us how large might be the spread of possible values if we obtain different random samples. Beta 1 hat may change, and variance shows us how large might be the spread of these possible values. Let's look at this variance of beta 1 hat. It depends on the variance of x in the denominator. If variance of x is large, then variance of beta 1 hat becomes smaller. Practically, it means the following. Yeah, sorry. Yeah, so let me continue this thought, and then we will go back to the previous slide. So we can observe that this sigma squared of beta 1 hat decreases if variance of x increases, which means that we want to collect such data where x has a large spread. If x deviates much in the data, then it gives us a chance to obtain a precise value of beta 1 hat, which is going to be close to true beta 1. So when collecting the data, make sure that the range of xi values is large, because it will give us large variance of xi, and given large variance of xi, variance of beta 1 hat is going to be smaller, and it makes our calculations precise or more precise. On the other hand, in the numerator, we have variance of x times u, which is the covariance between x and u also. But what is the most important is u, this term. If we leave a lot of other factors, and these other factors influence the outcome variable y, then the precision becomes poorer. So that's why if variance of u decreases, variance of u goes down, then this variance of beta 1 hat also decreases. So we want to have, let's say, tighter scatter plot around the population regression line. If you remember the scatter plot, and if the scatter plot looks like a circle, it means that variance of u is large. If this scatter plot looks like some ellipse, or it is at least somehow tightly distributed around the line, then the precision of our estimation is going to be good enough. So these are two practical implications why we are talking about this sigma squared of beta 1 hat. So first of all, we want the spread of x to be large. Second, observing the scatter plot, we want the scatter plot to be tightly distributed around the line. If it's too wide, then the variance of beta 1 hat is going to be large, and the precision of our calculation is going to be small. And now let's go back to the previous slides. So if we claim that in large samples, for example, the sample mean has a normal distribution with some expected value and some variance, and expected value is mu of x, and the variance of mu of sigma squared x must be divided by n. So it's my mistake. Must be divided by n. Yeah, so following the same logic, we can say that beta 0 hat is normally distributed with the expected value of beta 0 and the variance, which is presented here. This is the way how we calculate variance. and it must be variance, it's not error. And beta 1 hat is also normally distributed with beta 1 as an expected value and this expression as the variance of beta 1 hat. And now, if we know the distributions of these sample estimators, we can use confidence intervals, we can use hypothesis tests, because we know the distribution and we know the parameters of this distribution. The question is, so now going back to the to this discussion about the variance of x and the variance of beta 1 hat. So look, if we have, for example, these points, only blue points, and if we try to calculate to estimate beta 1 hat, it will give us a poor precision because look, the range of x values is small. If you take the wider range of x values, like from here to here, then the precision is gonna be larger. So this is what we want from the data. When we start the estimation, and if you remember when we also started working with the example data set, we started with the descriptive statistics. And in descriptive statistics, we observed what is minimum, what is maximum, what is the first quartile, empirical quartile, what is the median, whatever. So all these analysis basically is needed to ascertain that the variation of your variable x is large enough in order to make sure that the estimation of beta 1 is gonna be precise. This is basically the simple rule. So the wider is the distribution of x, the better is gonna be your result. And now,
Sorry, maybe you ask or you answer like, what is HI? Like, is there a name for it?
no, this is
Maybe.
just a way to simplify this expression. So if you take this and plug it here and here, it's gonna be a disaster. So just some repetitive thing inside the variance of beta 1 hat, which was extracted and separately shown. No, it doesn't have any practical sense. No,
Yeah,
just a way of calculation. So by the way, since we are on this slide, can anybody say what is the problem with getting this sigma squared of beta 1 and sigma squared of beta 0? So except for, let's say, awful form of these formulas. So suppose that we have a data set. We already know beta 1 hat, beta 0 hat. We calculated them manually in the exercise session. So suppose that next week in the exercise session, we also try to estimate these sigmas, to calculate the sigmas. What is the problem with the calculation? Or what might be the problem with the calculation?
unknown error term.
U is not known. By the way, variance is also not known, because this is a variance. This is the population variance. And we want to estimate this variance with the help of sample variance. Mu x is not known. So we have a lot of unknown parameters. So the whole variance of beta 1 hat depends on the population parameters of x and on the population parameters of the linear regression model. So be careful with this, please. This is mu x. This is the true population mean of x. This is ui. This is the error term which is not observed. And the variance of the whole thing is also not known. As well as here, this mu x is not known. And the expectation of xi squared is not known. So we need to switch all these elements with their sample counterparts, sample variance, sample mean, residual, you had here also sample variance of x, and so on. And then only after this substitution, all population parameters with their sample counterparts, we will be able to calculate. And now the question is that we are not able to calculate sigma squared. We are able to calculate sigma hat squared, right? So it's going to be the estimator of this sigma. So please be careful with this, and please try to understand what we are doing. So these variances are also population variances of beta 0 and beta 1 hat. These are not known variances, and we are going to estimate them. You see how complicated our life becomes. But once we understand this, and once we are able to substitute this variance with the sample variance, this residual, this error term with the residual, and all the things, that's going to be not that difficult. Just the calculation process is going to be long. That's basically what we are going to do in the exercise session. Well, finally, we know what are the sampling distributions of beta 0 hat and beta 1 hat, and we are ready to make the hypothesis test. So this slide is going to be the transition to the next lecture. So from statistics, we know that if we have a sampling distribution, we are able to build confidence intervals, and we are able to conduct hypothesis tests. So we know what is the sampling distribution of beta 1 hat. Once again, yet we don't know this variance, and this variance must be estimated using the appropriate methods. And well, if we know this, we can construct this thing. So how do we call this type of statistic? If it's a normal distribution, and if here we have a population variance, that's going to be Z statistic. Yes, if we know the population variance, that's going to be Z statistic, which is going to be standard normal, which is going to have the standard normal distribution, 0 and 1. And then we can, with the help of this Z statistic, make some hypothesis tests. But sigma squared of beta 1 hat is not known. We must estimate it from data. Therefore, with the help of sample variance, we arrive to the t statistic. If in the denominator we have a t statistic, then it has a student distribution, and all the methods applied to the student distribution also work. So, and this square root of sigma squared is going to be called the standard error of beta 1 hat. So this is what we are going to do in the next lecture. We will, in the next exercise session next week, we will make the estimation of this variance. We will try to calculate this from the data, and then, knowing how to do this, in the lecture 2 weeks after, we will talk about the hypothesis tests and about confidence intervals related to beta 1. So, the conclusion. First of all, what we have studied today. We know 3 assumptions. The first one is the most crucial assumption. If we want to give the causal effect interpretation to beta estimates. So basically beta 1 hat is more important for us. With the help of these assumptions, we know that OLS estimators are unbiased, which is also an important thing for practical implications. So we know that under these assumptions, estimators are normally distributed in large samples, which gives us a chance to conduct statistical hypotheses and build the confidence intervals about population parameters beta 1 and beta 0. Any questions related to this material. So based on your answers, first of all, I see that you understand what's going on, which is nice. And thanks for the wider participation today. Any questions regarding this material?
It was
Not
clear.
really.
Perfect. Then the last thing, home assignment number 1. So it will depend on my performance with your midterms. I mean, so first of all, I am going to check your midterms, and then I will make this home assignment. So I hope that the home assignment is going to be available on Monday evening, probably. But still, as usual, it's going to be available till Sunday evening. And this home assignment is going to be based on the same things that we did last exercise session. You have a data on X, on Y, and with the help of this data, you need to calculate beta 1 estimate, beta 1 head, and beta 0 estimate, beta 0 head, with one of 2 approaches that we used. I hope that's going to be simple, just some mathematical exercise for you based on the data. Yes, and one more thing that I wanted to tell you. So